Hi, my name is Joe Kliza. I'm going to help you learn AP Physics. And for some of you, that might mean introductory college level physics. Now, let me show you two things. The first is about a 6-minute long video that I use to try to recruit high school students into a course that I teach called Honors Physics here at a local suburban high school near Chicago. And the second is I just want to show you a short physics lesson that I do on a whiteboard. Let's take a look. My name is Joe Kliza, and you should take Honors Physics. Don't delay, sign up today. Your life depends on it. Seriously, though, who wouldn't like honors physics? You get to talk about things like Chicago Cubs home runs, launch angle, projectile velocity and distance, forces, g-forces and the effects on the human body, orbits in outer space, Einstein's theory of special relativity, general relativity, energy, momentum and collisions, waves, sound, electricity, magnetism, light, and optics. Reason number one, you're not sure, but there's a chance you might be interested in the field of engineering. Lots of jobs, lots of money, lots of opportunity. Physics is the gateway to engineering. Reason number two, you might be headed to the medical field. You can't get into med school without taking physics in college, and you don't want to take physics in college without taking a good honors physics course in high school. Reason number three, you might not want to be an engineer or headed to the medical field, but you might just want a challenging and fun class in high school where you learn a lot, not about just physics, but about learning in general and how to go about learning in new ways you haven't before. So for any of these reasons, honors physics might be a great course for you. And so over here you see a baseball bat. You guys have all played baseball, softball, in a PE class at some point. But this little X marks the spot is really important. It's called the sweet spot. And why in the world does it feel sweet when you hit a ball at that spot? Where I'm here to tell you today.
Well, what makes a sweet spot sweet? That has to do with something called standing waves. So what you're going to see me do is I'm going to send a wave from this end of the slinky down to that end of the slinky. And when it hits the wall, or hits the end there, it's just going to bounce back, and you'll see it reflect. Watch. There you go. So the wave went to your left, and then it came back to your right. Well, what I'm going to do is I'm going to keep on sending waves to the left, and the reflected waves are going to keep on coming from the right, and they're going to interfere. And as they interfere, they're going to make what's called a standing wave. And instead of a wave moving left and right like that, you're going to see a wave that's going to look like it's flopping in place and not really going anywhere. It's just a standing wave. So check this out. It takes a second to set up, so give me a shot. Here we go. There you go, check that out. We call this the third harmonic. And it looks like waves aren't moving to the right or to the left, but they are. They're just going through each other. And there's certain points called the nodal points where the waves are canceling out. That would be right at my hand, maybe a spot right about there, and there's another couple spots where the waves cancel out. And then in between those spots, there's antinodal points where the waves aren't canceling out, but they're getting really big. Right here we have a diagram of what you just saw with the slinky. We have what's called the third harmonic. I have 3 areas of constructive interference, which are called antinodes, and I have 4 areas of destructive interference, which are called nodes. And that's where the waves are canceling out. And that's the secret to the sweet spot. But before I tell you the secret of the sweet spot, I've got to show you a really cool demo. Check this out. I have a jigsaw right here that I took from home. And when I hit the button, it's just going to jig up and down, up and down. It's connected to this rope. And so it's going to make a wave on this rope just like I did with the slinky. But it's going to do it at a frequency higher than I was able to do it. So I'm going to go ahead and turn this on, and the wave is going to go down the rope. It's going to hit this end, bounce back, reflect with the new oncoming waves, and it's going to make a standing wave. And you're going to see something here that's probably about the 10th harmonic. You will see 10 antinodes. And it's pretty cool, but it's pretty loud. So watch out. Here we go. That was cool. Wait till you see it with the lights off and a strobe light. So that's a really cool demo. Now, how does that relate to the sweet spot? You take your bat right here. See, your bat's like this. But when the ball hits it at the sweet spot, that becomes a node, and where your hands are becomes another node. And the bat vibrates like that on either side. You can't really see it because the amplitudes are too small, but they're there. And with your hand at a node, no vibrations. You feel really good when you hit that ball. But it only happens when it hits there. And it's not true just for a baseball bat, but for a tennis racket as well. So that's physics.
So there you have it, honors physics. Now, you're not going to take honors physics from me at a high school, but you might want to be tutored by me. So let me give you a little taste of what a short screencast might look like on a topic called acceleration, a really complex topic, but I try to explain it in a simple way. And when you work with me, you'll get access to explanations like this. So let's take a look at that. All right, well, this screencast is going to help you all with acceleration, as well as something called the equations of motion and their use. Well, if you start off by asking somebody what they think of when they hear the word acceleration, they'll probably say something like a car speeding up, or it means gaining speed. Well, a really good scientific definition of acceleration is the rate of change of velocity. It's the rate of change of velocity. It would look just like this. A equals delta phi divided by t. Now, first of all, this t comes from the word rate. Anytime you use the word rate, you're saying a quantity is divided by time. So, for instance, speed is the rate at which distance is covered. Distance, rate, gives you average speed, right? Well, if we talk about the rate of change of velocity, rate means we're going to divide by time. And what are we going to divide by time? We're going to divide the change in velocity. And remember, that triangle there means change. It's that Greek letter delta. And we've got our v representing velocity. And this is going to equal acceleration. Now, we could also write this equation like this. A equals v minus v naught. When you hear me say the word naught, it's what scientists use to represent that, or to speak of that little zero down there. And that means initial velocity. This over here is a final velocity. And if you take the final minus the initial, why, you have the delta velocity, or the change in velocity. So really, these two equations, this one over here and this one, they're saying the same thing. And then what you're doing is you're dividing by the time interval. And this is how you calculate acceleration. It's the change in velocity divided by time, or it's the rate of change of velocity. Now, the car I happen to be driving right now is a Nissan Altima, and if I hit the gas or put the pedal to the metal, I bet I can go from 0 to 60 in 4 seconds. I don't know if that's true or not. Maybe I'll try it on my way home. But given those numbers, an interesting question would be, what is my acceleration over that time interval? Well, to figure that out, you're just going to go ahead and do acceleration is the change in velocity divided by time. Change velocity is final velocity minus initial velocity, or v minus v naught, divided by the time interval. In this case, my final velocity would be 60. My initial velocity was 0. And this is miles per hour. And then I'm going to divide by 4 seconds. And so when you get a calculator out and you use 60 divided by 4, you get 15. And the big question now is, what are the units? You know, the units for speed are miles per hour, or meters per second, or millimeters per year, or furlongs per fortnight, or something like that. It's any distance divided by time. But here, when we're talking about acceleration, we have some units that look like this: miles per hour per second. And those are really strange units. You can see that there's one type of distance there, and there's a couple times, but these are units for acceleration. So at this point, we probably want to ask, what does it mean to be accelerating at 15 miles per hour per second? Well, the key here is really thinking about what these units mean. These are units of speed, 15 miles per hour, and these are units of time, seconds. And what we're saying is we're going to gain 15 miles per hour of speed every second. Or another way to look at it is I'm going to change my velocity by a positive 15 miles per hour every second. So at the end of 1 second, my Nissan Altima is going to be going 15. At the end of 2 seconds, my Nissan Altima is going to be going 30. At the end of 3 seconds, it's going to be going 45. And by the time I hit the 4th second, I'm going to be at a whopping 60 miles per hour. And we're going to say, boy, did that thing accelerate. So that wasn't anything super exciting, but it was easily understood. And so when you work with me, I'll be explaining topics, but as I'm doing so, I'll be asking you questions all the time, questions to make sure you're tracking with me, and also questions that will help expose any faulty thinking you have so that I can correct it as we go. And we'll just, do lessons like that. And of course, at any point, if you just have a homework assignment you want to work through or a certain problem you're struggling with, I can help you work through that. And I'll lead you through it as opposed to just giving you an answer. So, anyways, so I hope those things are helpful for you to get an idea of who I am and how I work. And I really look forward to hearing from you sometime soon. Okay? Have a great day, and we'll talk to you later.